Okay. And you can look at me this way. You're good. First, name and title for me.
So I'm Dr. Daniel Hughes, and I'm Director of Bioinformatics for PMLS.
Wonderful. What's your background in education?
So my background, originally my undergraduate degree and my master's degree are essentially in structural biology, bioinformatics.
You can start over.
I say bioinformatics so often now, it's the word that comes out. So originally, my undergraduate and master's degree are in biochemistry from the University of Oxford. I then changed to essentially molecular biology and genomics, where I did a PhD in the University of Cambridge and in the Sanger Institute, which is where much of the human genome was done. I then actually changed and left science for a few years, and I was just programming. And then eventually I moved back into science, but at the infectious disease genomics side. So I worked for several years at the European Bioinformatics Institute as a bioinformatician, senior technical programmer, before moving to Baylor College of Medicine, where I was lead programmer for the originally genome annotation and assembly, and then eventually the cancer genome group. And then I moved to Columbia University, where I was originally a data science programmer, genomic data science programmer, and eventually was promoted to Director of Software Engineering and Genome Informatics. And then finally, Director of Cancer Knowledge Base, so essentially for clinical data, molecular integration in large-scale data mining for cancer genomics.
Would you say all of that helped you in bioinformatics?
Oh yes,
Yeah.
I've worked in pretty much every area of modern genomics there is at this stage.
So you know it all.
Jack of all trades, master of a few.
And how did you get into this field?
So originally, I did my PhD at the Sanger Institute just at the kind of end of the Human Genome Project. And so I was really a molecular biologist and genomicist. But in the Sanger Institute, which is where much of the actual computational biology was performed on the Genome Project. And so I was constantly exposed, and I was always a better programmer and this stuff than lab-based. And so eventually I kind of morphed more and more into the kind of computational biology direction.
All right. How was that transition like?
Originally, it was actually because after my PhD, I promised to go, I decided to take some time off and go and learn Portuguese in Brazil. And I moved to Brazil and I stayed for 3 years, and I got very interested in infectious diseases. And so that's actually what brought me back into genomics.
But that wasn't why you were there. You just wanted to learn Portuguese.
I wanted to learn Portuguese. I went for 3 months and I stayed 3 years.
Wow. And doing?
So programming and translating. And that's when I got interested in infectious diseases. And so I worked for what was actually a US government project called VectorBase. It's a NIAID-funded project. But most of the bioinformatics is done out of the European Bioinformatics Institute in Cambridge. And so I worked on the malarial mosquito complex, so malaria, dengue, all these other kind of nasty little critters.
Wow. Is there, like, what was your work in that? Like, how to spot them, how to mutate?
It was really looking for large-scale. This is back a while when it was much harder to look for variants. And so this is really about getting reference genomes so that we can understand the disease spreading process and how these actually, because these are all vectors, they spread the parasites such as the plasmodium or toxoplasmosis, etc. And so it's really understanding how these combinations and how these interactions work between these organisms and the actual disease vectors they're causing.
All right. And now that you're in bioinformatics, would you mind taking a step back and defining what it is?
So, bioinformatics is always a kind of slightly nebulous area, and the relation between it and computational biology, it can be a little blurred. Bioinformatics is essentially the large-scale computational informatics analysis of biological data and then trying to understand it. So it's kind of data mining, but specifically for large-scale, high-level compute and industrial level compute for understanding biology.
And how do you use bioinformatics here at PMLS?
So we're using bioinformatics in terms of how we can actually develop more consistent assays for looking at human disease diagnosis, human disease screening for a number of different complex diseases, but then we're also doing risk scores, so we can actually try and predict your risk score for any particular disease such as breast cancer, prostate cancer, diabetes, etc. And of course, we actually have the COVID element there, so we're doing a lot of kind of variant identification as well.
And what would you say are the benefits of having someone like you here on staff?
Essentially, there are areas where while certain areas of bioinformatics are moving more towards the kind of black box approach, you can just plug it in and play, we're still a long way from that in most areas of sequence analysis, especially when it comes to things like cancer, when it comes to things like prenatal diagnostics, when it comes to early diagnostics of undefined and rare diseases. We're still quite some way of actually being able to kind of have an automatic pipeline that runs end to end without any bioinformatics understanding.
Right, and some of those we already have, right? So is there anything else you're working on that
to some extent what we have is we outsource the bioinformatics at the moment, which essentially leaves you in an inflexible atmosphere, because one of the things is what you have to remember is there's actually a huge potential for reusing the data. And so when you outsource in this manner, you're basically doing one assay per project, whereas actually you can ascertain a lot more information, because when you're doing this analysis, you don't necessarily need to just say this person's diabetes risk is X, Y, or Z. You can actually look at diabetes, cardiovascular risk, and all of these different ones in the same time. And so why are we actually trying to go to one assay per diagnosis? We can use the same assay and then redivert the results as required.
And that's what we're working towards, or is it something we're already?
That's what we're working towards.
That's amazing. So in that aspect, what does your day-to-day look like as a bioinformatic director?
So essentially, because we're starting from fresh, it's basically end to end. So it may be from the actual design of the capturing panel, what regions of the genome are we sampling, through to actually developing robust QC mechanisms, and then actually variant interpretation. So how do we actually see, because every genome will have a number of different deleterious events, how can we actually say, well, what's your genuine risk of any particular disease, and then also, is this likely to be responsible for any of the actual phenotype you're displaying?
Wow. So that's like,
so it really is it's root to branch.
What are your goals with the R&D department?
So the R&D department, essentially our goals are to there's now a large move towards a sort of democratization of medicine and the actual ability to allow patients direct access to useful medical results so that they can actually interpret their own risks and understand it. And so they can kind of modify their lifestyle in accordance with this, or just understand what their risks are in future and how their risks of any particular environmental abuse or whatever it is, and so they can adapt their lifestyle, or just have a better understanding of what they need to avoid and how they need to modify their lifestyle.
Right.
What R&D does essentially is, so we have the large-scale production with established assays. R&D is looking at a lot of different other assays and how we can actually, what are the kind of unmet medical needs in the community, and how we can then turn these into something that we can actually provide patients with, and so that they can get a better understanding of what this particular medical need is and how they need to adapt to it, or if they need to get specialized care for it.
There's so much more noise now. Is there anything else that you are working on that maybe we're not aware of?
So essentially what we're doing right now is the large body of my time is actually spent on developing a new kind of large-scale panel that will allow us to work on multiple different diseases and disease risks. Then these kind of more complex disease risks, COVID variant analysis and new variant analysis and variant concern, and then also how do we scale our in-house COVID analyses, and how do we do the in silico analysis to show that our standard COVID assays are actually robust to new variants and will not actually stop working as these new variants emerge.
That's fun. How has it been for you working here with the R&D team, with the PMLS team overall?
It's great. It's a dynamic environment that's desperately eager to bring in new challenges and meet the kind of challenges of the next century's medical needs as they adapt, because they are adapting so quickly. I mean, you have to bear in mind 10 years ago, the first human genome took about 10 years and cost $500 million. With the machines we have over there, we can do probably 50 or 60 in a day or two. There's a kind of paradigm shift in the amount of data we're acquiring now. And really, the computational techniques are lagging behind the actual ability to acquire new data, and we need to fill in those gaps.
Oh, you're good, Eva. Go ahead.
So I'm dreadful.
Yeah, I know, you're okay. God, that noise. I think it's just going to keep going.
It's a tip washer, yeah? Yeah, that's going to go for a while.
Yeah. I didn't think about that. I hope it should be still fine. Is there anything else that you think we should know about what you're doing here that others should know about as well?
I think people should know that we are constantly evolving to meet the new medical needs as we find them, and adapting our protocols to make sure that we can actually adapt to new variants, we can actually identify new variants, we can look at different risk scores in the population. We're actually trying to screen and protect the next generation from the new risks in disease and healthcare.
That was beautiful, Sam. I loved it.
That was horrible.
That was beautiful.
That was horrible.
We're good.